You can use the concept of aromaticity or anti-aromaticity to explain why some molecules are more acidic than others. Remember, what it means to be acidic is to donate an H+. So for example, here you have a lot of H's. You have two H pluses on this right here. There's two, technically, on both of those, but let's just focus on one. If these were acidic, they would donate the H+. Now, it wouldn't take its electrons with it. It would just leave by itself and gain the plus sign, plus charge. The electrons that were in the bond, those would get turned into a lone pair, and they would give the carbon a negative formal charge. So, for example, if this molecule on the left behaved like an acid, it would donate that hydrogen. When it leaves, it wouldn't take the electrons with it. It would have the positive charge, and the electrons that were in the bond would become a lone pair. And the carbon there would have a negative formal charge. Now, what's the likelihood that each of those molecules will let the H+ get away? Because if it lets the H+ get away, it's a strong acid. If it doesn't let the H+ get away, it's a weak acid. They give us something of an answer at the bottom here. They give us these pKa's. If you remember, the smaller the pKa, the stronger the acid. Not only that, but remember that anytime you have that lowercase p, like as in pH, POH, pKa, that lowercase p means the negative log. You're really just taking the negative log to take a non-intuitive number, like 10 to the negative 16, which is really hard to visualize or understand, and turning it into an intuitive number, like 16. But one thing to remember is that the log solves for exponents. You take the negative log to get rid of the negative sign to make it even more intuitive, but the log solves for exponents, which means that two molecules that have a difference of 20 in their pKa's, when you're actually thinking about the difference in acidity, that's not just a difference of 20, that's a difference of 20 powers of 10. So this molecule on the left is profoundly more acidic than the molecule on the right. What could be explaining that? Why would the molecule on the left be 20 powers of 10 more acidic than the molecule on the right? And that's what they want you to explain here. So let's go back to our scenario. These hydrogens are trying to leave the molecule. If they leave, the molecule is acidic. If they don't leave, the molecule is not acidic. Everything hinges on whether the molecule that's left behind is stable. If it's stable, then the hydrogen can get away, and what does this molecule care? It's stable by itself. But if it's not stable, then when the hydrogen tries to leave, this is so jittery and crazy, so high in energy, that it snaps right back on. The negative charge is so intense that it attracts the positive charge of the hydrogen snaps right back on. It never leaves, and the molecule doesn't behave as an acid. So really, the acidity of these molecules boils down to the stability of these rings, and that depends on aromaticity. So let's start with the molecule on the left and go through the same thought process we've been going through in the last few videos for determining whether a molecule is really stable, aromatic, or really unstable, anti-aromatic. And the first question you want to ask yourself is, are there parallel p orbitals on all of these carbon atoms? Well, we know that the carbons that are involved in pi bonds have parallel p orbitals on them. So that takes care of all the atoms but one. We also mentioned in the previous video that positive charges and lone pairs can exist in p orbitals. So this lone pair here could be flying around as a p orbital shaped wave. And in that case, notice all of the atoms here have parallel p orbitals all the way around the ring, and you satisfy that first question, yes. So we go on to the second question there. The second question is, the number of electrons in the ring, does it fall in that pattern of 4n plus 2? So let's see how many we have in this molecule on the left. 2, 4, and 6. Remember, the lone pair was in a p orbital, so that counts. So 2, 4, and 6. We have 6 electrons flying around the p orbitals of that molecule. Is that summarized by this pattern? It is. If you plug 1 in for N, then you get 4 plus 2, that's 6 electrons. And because the p orbitals there do have that Huckel's number, 4n plus 2, of electrons in the p orbitals, the molecule on the left is aromatic. In other words, it's very stable. Compare that with the molecule on the right. We go through the same thought process. First, are there parallel p orbitals on every atom all the way around the ring in this molecule on the right? And there are. You have parallel p orbitals on all the carbons that have double bonds, and you have the lone pair exists in a p orbital. So every atom in that ring has a p orbital that it can put parallel to the atoms next to it. So yes. Next question. Are there 4n plus 2 electrons in those p orbitals? We have 2, 4, 6, 8. 8 electrons. That is not in the 4n plus 2 series. So if n is 1, then you have 6. If n is 2, then you have 10. 8 is skipped over. It is not in that series. And therefore, the molecule is going to be very unstable. It will be anti-aromatic. And so, if we go back and think about the acidity, this molecule on the left is very stable. So what does it care if the hydrogen leaves? Not at all. It's going to be perfectly stable as it is. And so that molecule will be able, the molecule we had, will be able to donate hydrogens to the solution because the molecule that's left behind is very stable. And so it has a relatively small pKa. Remember, the lower the pKa, the stronger the acid. For the molecule on the right, this was anti-aromatic. It's very unstable. So if the hydrogen tries to get away here, the molecule can't handle it. It snatches it right back. And so the hydrogen doesn't leave, and the molecule is not very acidic. It has a high pKa. So you could see how you could use aromaticity to determine the aromaticity and anti-aromaticity to determine the acidity of conjugated ring systems.